Okay, now we're on to step 2. And again, we're just talking about these in our generic format. We'll come back and plug in a specific problem out of the book in just a moment. So step 2, determining the value of our critical T's to define our critical regions for significance. Well, it's still a t-test, so we're using the same table that we used in the last chapter, that t-distribution table. And we're using, it'll be the same one in the next one, t-tests or t-tests essentially. I'll use the t-tables. So there are 3 things we have to know to use that table. Of course, we have to know how many tails our test is. So right now we're talking about 2-tailed tests. Oops. Of course, we've got to know our alpha level. Are we working at 0.05 or 0.01? And as we learned last chapter, the other thing we need to know is how many degrees of freedom we have in our test. Those are the same three things we need to know this week. But here's the little difference. The degrees of freedom is sample size minus 1, right? We know that that's sample size minus 1. But how many samples are there? There are 2 samples, right? 2 independent samples representing 2 independent populations. So if we just did this, we would have the degrees of freedom for 1 sample, but we'd be completely ignoring half the study that is represented by the other sample. So we're going to calculate this just a little bit differently in that what we want is the degrees of freedom for the total study, not just for 1 sample or the other sample. We want the degrees of freedom for the total number of subjects in there. So I'm going to just put a little t down here for total. We don't normally put that in there, but just to make it clear right now. So this value we want, you get that by getting the degrees of freedom for the first sample and adding it with the degrees of freedom for the second sample. So you get these degrees of freedoms just like normal, n minus 1 and n minus 1. But we get the degrees of freedom for each sample separately and then add them together. And that gives us our degrees of freedom for the entire study. So this is the one that we want to use on the table. This is the value we'll use to report in our APA decision in step 4 when we get to that. So remember, it's not 1 sample or the other. We want both sample degrees of freedom added together to give us the degrees of freedom for the study. And that's the one we'll use to look up on the table. Other than that, we use the table exactly the same way we always do. There's no changes to how we use that table. If the degrees of freedom value you're looking for isn't there, what do you look for? Which value is closest to what I need? Use that one. If there's a tie, what do? Go to the one that gives you the largest t value, right? Same rules all semester long for those tables. So that's step 2. Not really anything else to do there. So now we can move on to step 3, doing our calculations. Well, in chapter 9, there were 3 values we needed to know. We needed to know what the sample variance was, because we were using that in place of population variance. We needed then to use that value to calculate estimated standard error, because we needed that value then to calculate our T-statistic. We still need those 3 things. We need a measurement of variance and a measurement of error, and then our T-statistic. It's still those 3 things. But we have to approach it slightly differently, of course, because we have 2 separate samples to take into account. So the first calculation that we need to make isn't just for regular old sample variance. It is for what we call pooled variance. Pooled variance is very, very, very similar to the concept of the weighted mean we talked about back in chapter 3. So remember, for the weighted mean, we said if we had a sample mean for one group and a sample mean for another group and we wanted to put them together, we had to do that in a way that was fair. And how did we define fair? That we had to take into account whether the groups were the same size or not. That we found that if a group weighed more, it had a larger number of scores, it had more influence over the results. It had more gravity, is the way I described it in class once. And so that weighted mean would end up getting pulled towards that larger group. Same thing with pooled variance, only it's with sample variances. So we have the sample variance for one group, one sample. We have the variance for the second sample, and we need to combine them because it's all just one study. It's all one experiment. So we have to take these variances and combine them. But again, we have to combine them in a way that's fair based on the sizes of the samples. So absolutely go back and look at your quizzes from chapter 3 and look at those questions about the weighted mean. You're going to find questions very similar to that about pooled variance. So if we know the variance for one sample and if we know the variance for the other sample, we could take the same shortcut we talked about in chapter 3 if both groups weigh the same, if they both have equal sample sizes. You could just average those numbers together and be done. But otherwise, we need a formula to compute pooled variance. So our symbol for pooled variance starts with our symbol for sample variance, but it's not just for one sample, it's for combined or pooled samples. So we put this subscript of a P down there. So it has both a superscript and a subscript. So when you're taking quizzes or whatnot online for this, I really don't think you're going to find a symbol for that. Just type pooled variance when you're having to report these things. The equation for pooled variance is much like the equation for just straight up variance. Sums of squares divided by degrees of freedom, right? But we have two different groups. So we're simply going to take this formula and double it up. If we just look at it in half, that's just the formula for variance that we always had. But there's two groups, so we're doubling the formula up. The number one mistake that students make here is that they split this into two different fractions. They want to compute this fraction and then compute that fraction and add them together. Notice that there's one divisor line here. So we need to add together both parts of the numerator first, then add together both parts of the denominator second, and then divide. We don't divide until last in this case. So one of the ways to remember that is that this is the first calculation here, the first formula we need to run in step 3, and it is also one big fraction. So the first calculation is one big fraction. So in doing this, we will have fairly combined the variances for each sample that takes into account through the degrees of freedom their sample sizes. So we'll get a measure for variance for the overall study this way. And that's what we need to use in our next calculation. Our next calculation, again, is we need to calculate error. It's still called the same thing. It's still called estimated standard error. And as a definition, it still mostly means the same thing. What we've been saying up until today is that either standard error or estimated standard error tells us how much difference to expect between a sample mean and a population mean based on random chance alone. But we're not comparing a sample mean to the population they came from. We're comparing a sample mean against another sample mean. So it's just a little tiny alteration. So for independent measures t-test, estimated standard error measures how much difference to expect between two different sample means based on random chance alone. Now the definition is basically the same, the term is the same. We have to change the symbol to represent that we're not calculating the difference between a sample and a population, but between two different samples. So the symbol here is probably one of the wackiest symbols of the semester in a way. So in chapter 9, it looked like this, right? Because we were looking at one sample mean, capital M, sample mean, versus its population. But again, I'm comparing two different sample means now. So in this subscript, instead of just an M down there, the first sample mean and the second sample mean. So it's got a really long subscript for this, but it's still called estimated standard error. The formula for it is, again, pretty much like last week's formula and the week before that, but we have to take into account that there's two groups, not one group. So what we had last week, let me write it down here real quick, for just estimated standard error for a sample mean versus its population, we had sample variance divided by sample size, and then we square rooted that. Well, we're going to take that and just modify it for this week's chapter. We don't want to put sample variance in here because we just in step 1 of our calculations, in the first formula for variance, we calculated a pooled variance, a combined variance. That's the value we want to use. So we are going to look for pooled variance divided by the size of the first sample plus pooled variance again divided by the size of the second sample, and then square root all of that. And so again, you can see it's almost the same formula. It's just using pooled variance instead of a sample, because we've got 2 of them, and it's doubled up into 2 parts. Now, it looks weird. It looks like maybe I'm having some kind of corona bread stroke, maybe, that pooled variance is the same numerator. That is the way it is. Once we do the first calculation and get pooled variance, that's the only variance number we care about anymore. So we want that overall variance. So the overall variance is and divided by the number of scores in the first group, plus the overall variance divided by the number of scores in the second group. Notice that unlike the first calculation, this is 2 separate fractions. First compute this fraction, then compute this fraction, and then add those 2 values together, and then get your square root. So the first calculation, it's 1 big fraction, I said. The second calculation is 2 separate fractions. So again, that's sometimes the way I used to remember these. The first calculation is 1 big fraction. The second calculation is 2 separate fractions. Now, that gets us our value for our estimated standard error. Once we have our estimated standard error, we can go to our third and final calculation, which is for the T-statistic itself. Again, this is going to look a lot like the formula from last chapter. We just have to double everything up. So for our T-statistic, we're going to be, what we had before was sample mean minus population mean, right? But we've got 2 different samples representing 2 different populations. So if we wanted to be really formal about this formula, what we would write is that it's sample mean 1 minus sample mean 2. The difference in those samples as compared to population mean 1 minus population mean 2. And then all of that divided by our estimated standard error. Well, that's quite a bit, but here's the thing. Let's go back and think about what I said in step 1 about our hypotheses. Let's look at what we would have written for the null hypothesis for any one of these problems. That the value for the treated population mean 1 minus treated population mean 2 equals 0. What that tells us is this value here is always going to equal 0. So what that tells us is any calculation here minus 0 isn't going to have an impact. So conceptually, this is what's happening in the test. But when it comes to actually doing the math and actually performing the test, this is what I often call a statistical appendix. It exists, but it's not really doing much for you. We can remove it and it won't hurt anything because its value is always worth nothing. So when we're actually making this calculation, all we need for this formula is the first part of it. Sample mean 1 minus sample mean 2 divided by estimated standard error. Notice that it's built the same way, as I've said so many times, as all other statistic formulas. In the top, how much difference do I actually see? How much difference did I actually measure? And the bottom says, yeah, but how much of that difference is just due to random error? So it's the same ratio of elements as always. So we don't need to worry about the rest of that equation. I won't ever write it out again, but I wanted you to understand why that exists, particularly when you're looking at it in the book. It's there conceptually, that's a comparison that's being made, but mathematically, it's not something we have to deal with at all. So that's our formula for the t-statistic, very simple. Subtract the two sample means, sample mean 1 minus sample mean 2, divided by your error. You've got your t-statistic, which of course is going to tell us where our differences are located. And then of course in the end we get to step 4, where we report our decision. And again, we've only got 2 decisions all semester long. We're either going to reject the null hypothesis or we're going to fail to reject it. If we land inside the critical regions, if our t-statistic hits those targets, we're going to reject. If we miss, if we're in the body, if we miss the targets, we're going to fail to reject. Same as always. Now, writing this in APA format is also basically the same as last chapter. And again, I'm just writing this in the generic format. Some of you have been writing the generic format for the answer on quizzes. This is just a template. This isn't the answer, right? So it's our t with our degrees of freedom equals our obtained t-statistic, the one we calculated, not the one we looked up, semicolon p. If we reject, it's less than. If we fail to reject, it's greater than. And then our alpha level. Just remember, this degrees of freedom value here is the one from step 2, the combined one. Degrees of freedom from sample 1 plus sample 2 put together. That's the one we're going to see right here. So those are our 4 steps. So in the next video segment, we will go ahead and walk through an example.